Dr. Brian Miller received his BS in physics with a minor in engineering from MIT and his PhD in complex system physics from Duke University. Duke just lost to the Jayhawks. I wasn't going to point that out. I'm sorry. He's spoken internationally on the evidence for design in science, and he's a leading expert in the design arguments as related to the origin of life. He also helped write the books for God's Not Dead and Man, Myth, Messiah. He's spoken on stage with such experts as Josh McDowell, William Lane Craig, Michael Behe, Douglas Axe, and Stephen Meyer. He currently works at the Center for Science and Culture at the Discovery Institute, where he coordinates research at universities around the world related to the evidence for design in biology, chemistry, and physics. He was also a technical consultant for an innovative incubator, and he is leading a group of engineers and biologists who are studying where engineering concepts apply to life and where life exceeds the capacities of human engineering. Speaking to the topic, the origin of life versus the origin of species, how neo-Darwinism has failed, please welcome Dr. Brian Miller.
Thank you so much. It's such an honor to be here. And my first 2 years at Duke University, Duke won the national championship. So I don't feel too remorseful that they lost tonight. So I've already been there, done that. But tonight what we're going to do is talk a bit about the origin of life. And the reason that topic is so important is that, we need the slides up. The reason this topic is so important is because it really deals with the issue of whether the universe and life are the product of a designer, an intelligence, or simply a product of the blind forces of nature. And really that question is one of the most important questions you can ask because it defines everything about how you live, about your future, and about society. And also the origin of life is really important because that is essentially ground zero for this discussion of design. Because I will argue, one, that it's an impossibility for the blind forces of nature to bring about life, and two, we see very, very clear, unambiguous evidence for design. So those are the two things I'm going to talk about. But I need to begin to talk about what essentially is the theory of origin of life, or what are the theories? And the basic idea is you have some pond billions of years ago, and what happened is you've got some gases in the atmosphere, perhaps carbon dioxide, methane, different things. And then you have maybe some energy source, like lightning, maybe energy from a thermal vent. And what happens is you get the basic building blocks of life. And just to give you a quick Chemistry 101 course, the building blocks of life would be things like amino acids, which form proteins, things like nucleotides, which form DNA and RNA, which stores the information for the proteins in other parts of your cell. It's like where the instructions for your cell are. Things like lipids, which form your cell membrane, and carbohydrates, which could be part of the metabolism and the structures that store energy. Now, what happens is if you look at different theories of the origin of life, what you find is there's some major challenges. And I'm first going to talk about the thermodynamic challenges, and I'll explain that in more detail. But first, let's talk about how do you get the building blocks of life? One of the most famous experiments was called the Stanley Miller experiment, where they basically took reducing gases like hydrogen, ammonia, nitrogen, and what they did is they zapped it with electricity, and what they found is some basic amino acids formed, which is really encouraging. But what happened is when people started to understand, atmospheric physicists, geologists, what were the gases on the early Earth, they repeated the experiment, and they didn't get a whole lot, maybe a few amino acids. So what they had to do is they had to tweak the experiment, maybe put more hydrogen, maybe adjust the parameters, and then they got more amino acids. But that's about it. What these experiments have shown is that it's extremely difficult to produce things like nucleotides. In fact, the only experiments that have been able to reproduce nucleotides, which are like the building blocks of RNA and DNA, have had multiple steps, where the different steps have had to purify what was from one step, concentrate it, change the conditions, and then eventually, after many, many, many steps, you're able to produce like a nucleotide or something like a lipid. So these experiments demonstrate the difficulty of the building blocks of life. Now, the amino acids are challenging because in the best experiments, even with tweaked conditions, you don't just simply produce amino acids, but lots of byproducts. And the problem is, One of the major stages of the origin of life is to take amino acids and to create long chains of them, or to take nucleotides and create long chains. But the problem is the byproducts will interact with the building blocks and prevent these long chains from forming. So it's enormously difficult. But I just want to give you a sense of how difficult these experiments are. This is Robert Shapiro, who's one of a very well-respected origin of life theorist. And what he said is that an analogy that comes to mind is that of a golfer who, having played a golf ball through an 18-hole course, then assumed that the ball could also play itself around the course in his absence. He had demonstrated the possibility of the event. It was only necessary to presume that some combination of natural forces, earthquakes, wind, tornadoes, and floods, for example, could produce the same result given enough time. And that's the challenge, is a lot of people will appeal to origin of life experiments, but the experiments that are actually successful are the ones that are incredibly highly orchestrated, so they really demonstrate the need for design. Now, another very famous researcher is James Tour, who's one of the top organic synthetic chemists in the world. He creates very complex organic molecules. And he researched basically the whole gamut of origin of life theories. And this is what his conclusion was. He says, from a synthetic chemical perspective, neither I nor any of my colleagues can fathom a prebiotic molecular route to the construction of a complex system. We cannot even figure out the prebiotic routes to the basic building blocks of life: carbohydrates, nucleic acids, lipids, and proteins. Chemists are collectively bewildered. Hence, I say that no chemist understands prebiotic synthesis of the requisite building blocks, let alone assembly into complex systems. So what you find is people who are really honest about the origin of life recognize that nobody has any idea what could have happened because it's so difficult to just get the building blocks of life. I'm going to ignore those problems. There's actually another significant problem, and that's, let's imagine that you have a dream scenario on the early Earth, so the ideal conditions at the ideal times. The problem is perhaps you could create amino acids on one part of the world, you might create nucleic acids on another part, perhaps carbohydrates on another part, but then the challenge is you might be able to create a cell membrane somewhere else, but how do you actually get all of these pieces in the same location at the same time? And then the question is, how do you actually get them inside of a cell membrane? Because the problem is, a cell membrane, for it to support life, has to allow the right materials in, not any other material that could be destructive, and then once the materials are inside, they can't escape, because if they could escape as easily as they could enter, you wouldn't be able to build up the needed building blocks. Plus, you've got to allow the waste to escape. So getting a cell membrane that allows for that is virtually impossible, incredibly difficult. I will also ignore that problem, because there's an even more serious problem, and that deals with the issue of the thermodynamics. Now, let me explain to you step by step why this is a problem. Well, if you listen to origin of life critics, often they'll talk about the origin of life almost like rolling dice. So they talk about what's the probability, if you have all the building blocks, that those building blocks can come together properly to create a cell. So it'd be like you roll a dice and you get a 6, and that's like 2 amino acids formed properly. You roll another 6, and that's 2 more amino acids come together properly. You roll another 6, perhaps a few nucleotides come together. You roll a 5, and you have the wrong chemical reacting at the wrong time with the wrong molecule, and suddenly everything falls apart, and you have to start over from scratch. So Fred Hoyle talked about, in this model, what's the likelihood of life forming by chance? He said it's something like 1 in 10 to the 40,000. Now, for those of you that don't really like big numbers, 1 in 10 to the 40,000 is almost like rolling a dice that's 10-sided, and you roll the dice 40,000 times, and you get 40,000 tens in a row. He also used the analogy, it's like a tornado going through a junkyard and throwing all the pieces of debris in the air and having a 747 airplane land ready to fly. Now that's kind of interesting, but let's use a more pertinent example. Imagine you're watching Duke University next year, where they hopefully won't lose in the Elite Eight, And what happens is every single game, for every single point, the person throws the ball to an individual, and in one shot, they score a basket. From 90 feet, from 70 feet, it doesn't matter. Every single shot for every single game for the entire season. That's the likelihood of the building blocks of life coming together to form a functional cell. Now, most origin of life researchers know that it's essentially impossible for life to come together by chance. They know that. So what they hope for is that there's natural physical processes that will bias life to happen. Now, to understand that properly, I need to get into the idea of entropy for you to really appreciate this challenge. Now, let me explain to you what entropy is. What happens is when you're dealing with what's called a macrostate, like water would be a macrostate. It's just some sort of macroscopic state of matter. Now, what happens if you freeze water and you look at what's happening microscopically? Where is every atom? What's their momentum? How are they interacting? That is a microstate. So a microstate is what every single atom is doing in water at a given time. What happens if you look at all the possible configurations of water, the water molecules, and that number tells you the probability of water happening versus, let's say, ice or the water is a gas. So n is the number of microstates that relate to water. Now, if you look at the probability, obviously the probability is inversely related to the number of states. Now, here's the key. Entropy relates to the number of microstates that are associated with a macrostate. Technically, it's the natural log, but don't worry about that. So in other words, water has more entropy than ice because there's a larger number of ways the atoms can configure themselves for water as compared to ice. That's simply what entropy is. Now, you may have heard the idea of the second law of thermodynamics, and that's the idea that nature always goes from low entropy to high entropy. And all that means is that nature wants to do what's more probable as opposed to what's less probable. That's all that means. Of course, if it was simple as that, the question is, why do we get ice? Because when I talked about that definition of entropy, I assumed every single microstate or every configuration of water was equally probable. That's what I was assuming, but that's not necessarily the case. Because what happens when you deal with ice is you have the positive attraction, or you have the attraction of the hydrogen with the oxygen. So the force of attraction forces the water molecules to form ice. So what happens is nature is biased towards ice because of that positive attraction. It essentially goes to a lower energy state. As an analogy, if you imagine rolling dice, you would never get 1,000 sixes in a row unless the dice were loaded. So if the dice were strongly loaded, it might be very easy to get 1,000 sixes in a row. And in this case, the dice are loaded in favor of ice over water, at least at low temperatures, which is why water takes place. Now, when you think about these ideas, that gets into the issue again of what does nature want to do? Now, nature wants to go typically, under all normal circumstances, from low entropy to high entropy if all configurations are roughly equal. Now, often people talk about the idea of going to higher entropy as going from order to disorder. Now, that description is not perfect, but it is helpful in some ways. And let me use an analogy. If you think about, is it easier to keep your room neat, or is it easier to keep your room messy? Now, do you happen to try to keep a messy house, but every time you come back it tends to be neat? Not likely, unless you're married to a very kind husband or wife. Now, usually your house will naturally go from neat to messy. And that's why they use the analogy of order versus disorder. The idea of your room being messy or disordered means that there's a lot more ways, a lot more possible ways that your house could be messy than neat. And because there's more possible ways, that's why you define a messy room as more disorderly or having higher entropy. That's just an analogy, but that's just sort of an idea to get a better picture. So again, as I mentioned, nature tends to go from low entropy to high entropy but not always. And I used the example of water becoming ice. And that's because there's a second driving tendency in nature. And that's the tendency to go from high energy to low energy. Water runs downhill. Water doesn't run uphill. And again, the energy tells you how the dice are loaded, because nature is biased towards states of lower energy as opposed to higher energy. Now, this is significant because if you think about the origin of life, life is both highly ordered and life is very high energy. So that's kind of like trying to roll 1,000 dice in a row if the dice are strongly loaded towards lower numbers, like in a 1 or 2. So it makes it even more difficult than if it's by chance. Now, what happens is chemists often talk about what's called the free energy. Same with physicists, but chemists use the Gibbs free energy. And the free energy combines the energy, or technically the enthalpy, and the entropy. And as this equation shows, entropy typically dominates at high temperatures. Things go to high entropy at high temperatures. And energy dominates at low temperatures. Things go to lower energy at low temperatures. But in no circumstance, in no conditions, will you simultaneously go to both high order or low entropy and high energy. So from this analysis, the origin of life seems to be physically impossible. However, there is one loophole. And that's what happens in what's called non-equilibrium systems. So if you talk to an origin of life theorist, they'll often say, maybe this is true if you're near equilibrium, but what if you drive the system with lots and lots of energy, and you move the system far from equilibrium? Maybe the energy can help to overcome the free energy. And people often will use examples. For instance, if you look at, let's say, boiling water, and you heat the water from below, and you cool the water from above. What happens is you get roll patterns because the flow of energy through the system creates what's called self-organizational order. And people say maybe the order in this system is somewhat similar to the order in a cell. Another example would be that of a tornado or a hurricane, or perhaps it's called the Beasley reaction, where you get these pretty patterns if it's driven far from equilibrium. So the idea is if you give lots of energy to the system, maybe that can create order. Well, the problem is the order you see in these systems is completely different from the order you see in a cell. The order in like a tornado is dynamic. There's particles in motion. It's large scale. You can see the funnel cloud. While the order in cells is microscopic, and the order in cells is going to lower entropy, while the order in a tornado at the macroscopic level is more ordered, but at the microscopic level, these systems always generate entropy. So they always go in the wrong direction. And to speak about that more formally, what happened is there's actually been research done on systems far from equilibrium, and that's what's called fluctuation theorems. And this has been popularized by a man named Jeremy England from MIT, and he looked at systems that were driven very, very far from equilibrium, like the systems I showed, and he said, what's the probability of going from some macrostate 1 to some macrostate 2? That's like going from water to ice or ice to water. What he found is that even far from equilibrium, nature still wants to go to higher entropy, and it still wants to go to states of lower energy, even far from equilibrium. What that means is that the probability of life forming, even far from equilibrium, is astronomically improbable. It's like 1 in 10 to a billion. Those are like calculations by people like Harold Morowitz and some others that I'll show you. And again, just to give you a sense of how small that number is, 1 in 10 to a billion would be like a basketball team, which every play, they throw it to a person, they score immediately, not just for 1 season, but more like for 1 million seasons. It's completely impossible. So that's the situation. So there is, at this point, no possible way that life could form purely by chance in the laws of physics, either near equilibrium or far from equilibrium. So let me summarize my points. Or let me use one analogy. For those of you that may not be into the science, you can wake up, you can stop looking at the shows, and this is for you, for those of you not into science. Let me use a simple analogy. Imagine you go to a library, and the library has lots of books on the floor. It has some books on shelves. A lot of the books are scattered, but some of the books are nicely stacked. What happens is the higher shelves are like higher energy. Neatly stacked books are like lower entropy, while books scattered across the floor are like higher entropy. There's one more issue too. In life, it's not enough to have structures in low entropy, but you have to have things in the proper configuration. You've got to have molecules in the right order, like in proteins, and I'll go into that more. So it's more like you've got a bunch of books that are in alphabetical order by last name or the Dewey Decimal System. It doesn't really matter. So life is like having a lot of the books on the top shelf, neatly stacked in the right order, either alphabetical or the Dewey Decimal System. So the problem is, what happens if you start to drive the system with energy, like there's an earthquake? Well, any energy will, at times, take a book on the floor and take it and cause it to jump to the top shelf. That will happen if it's a strong earthquake, but what's much more likely to happen is the books on the top shelf will tend to fall to the floor, and anything that's ordered will become randomly scrambled. So what happens is nothing you can do will cause the books to go to the top shelf in the right order, but they will always tend to go away from the state that's synonymous with life. That's the problem. So let me summarize my points. First of all, what happens is life is too improbable to happen by chance. Almost all origin of life researchers agree with that. It's too improbable to happen by chance. The problem is, those arrangements which correspond to life are less probable than all possible starting states. So again, not only is it too improbable to happen by chance, it's much, much worse than just by chance. Because again, remember, the dice are loaded against life because life represents very high energy. So all natural processes move towards higher entropy and or lower energy, lower free energy, but the origin of life has to move in the opposite direction. And systems far from equilibrium are no more likely to generate the first cell, since they also tend toward higher entropy and the release of energy, or to lower energy states, while life requires the opposite. So that's an extremely, basically irrefutable problem. There's nothing that can get around that. But the obvious question then is, how does life do it? How does life reproduce? How does life live if what I'm saying is true? Because there is only one way around this problem technically, and that's with the use of machinery and information. That's how you can overcome free energy barriers. Well, what do I mean by that? Let me use an analogy. Let's imagine that you come home to your house after a long vacation, and your house is a total mess. Perhaps your children got out of control, perhaps friends snuck in and had a party, who knows? And you heard at an Origin of Life talk someone say, all you need is energy to create order. So you think that's great. So you put gasoline on your couch, you set it on fire, and you think maybe the fire from the couch will organize my house. Well, unfortunately, that's going to probably cause more problems than you started with, and you have to buy a new house. So after you buy a new house, a year later, you come back and you have the same problem. Your house is a mess. So you think, I'm not going to make the same mistake as last time. I'm instead going to buy a robot, because a robot has an engine, and that engine will convert fuel, either gasoline or solar radiation or electricity, into mechanical work. So the mechanical work then can be used to order your house. Well, let's imagine you buy your robot off Amazon, you charge it up, and you let it loose in your house. Well, there's a big problem. If your robot just makes random motions, it's going to cause more problems than what you started with. So what is the thing you forgot to do? You forgot to give it the instructions, the software, because you have to give it information so the robot knows what to do. So one line of code is like, wash the dish. Another line of code is like, vacuum the carpet. Now the machinery that processes energy and the information will allow you to order your house. Well, you see the exact same thing in cells. Because in cells what happens is you've got advanced molecular machinery, and this molecular machinery processes energy, either things like the flow of hydrogen or light or glucose. And what it does is it will turn the energy, like for sunlight in this example, into high energy molecules like ATP. So the machinery in life, like again photosynthesis, will create high energy molecules, and then those high energy molecules essentially act like batteries that give you the energy you need to drive the metabolism that you want. So in this picture, you have photosynthesis, which is driving the carbon fixation in some photosynthetic cell. Well, there's another problem. And the two questions I have then are, how do you get at that energy, and how do you know to drive the right reactions? Because if you look at the metabolism in a cell, you have lots of complex chemical reactions taking place, and you have to have the right reactions and none of the wrong reactions. And the problem is many of these reactions don't happen naturally. It's kind of like if you've got iron and oxygen, you can produce rust, but there's no way to go from rust back to iron because nature wants to go from iron to rust. But a lot of these reactions are like going from rust to iron. They don't happen naturally without help. In fact, here is an example of like the photosynthesis I showed you. Here's the carbon fixation in this much larger cycle. And people thought about how likely is it for a bunch of random atoms to come together and to create the right interconnections and the right metabolism to run life. And it's fantastically improbable. It'll never happen. So again, how does nature do it? And just to explain some of the difficulty, here's one chemical cycle, the citric acid cycle. And this simple cycle consists of numerous chemical reactions taking place. And all these chemical reactions have to take place at the right time and the right rate. And some of them need the help of ATP to move forward, or some high energy molecule. So how does it happen? Well, in life, you've got very sophisticated proteins called enzymes. And what these enzymes will do is these enzymes will grab the right molecules and force the right reactions to take place. And these enzymes might also grab an ATP or some high energy molecule, cause it to break down, and then use that energy to drive a second reaction in the right direction. They're incredibly sophisticated. So the question then becomes, how do these enzymes do that? How do these enzymes know to grab the right molecules and drive the right reactions? That's pretty extraordinary. Well, what happens is these enzymes are composed. Oh, there's a beautiful YouTube video called How Enzymes Work. I encourage you to watch it. It's called How Enzymes Work. But what enzymes are proteins, and these proteins consist of long chains of amino acids. So there's about 20 common amino acids, and the amino acids are like letters in the English language. In the same way, you have to have a lot of letters in a sentence for the sentence to make sense, and they have to be in the right order. A protein consists of a lot of amino acids in the right order, like the letters of a sentence, and that order or that sequence or that information in the sequence causes the enzyme to fold into the right configuration, which drives the right reaction. So everything in life is based on information. Okay, now for the people that aren't into science, you can come back. This is for you. So let me use a simple analogy. The information in life is kind of like alphabet soup. Who's ever had alphabet soup growing up? Now, what do you want to do when you have your alphabet soup? You want to stir up your alphabet soup, and what do you hope to see? You'd love to see a word. You'd love to see your name, right? It's like a sign from God if you see your name. Now, if your name is Bob, it's a lot more likely than if it's Stephen Oppenheimer Jinglemeyer Schmidt. You'll never see that if you are looking for your name in the soup. But what happens one day? If you're not feeling very well, you're kind of sick, so you go take your shower and you come down for breakfast, and you see this in your alphabet soup. It says, drink plenty of fluids and rest until you are feeling better. How many of you would think, oh, that's just an accident, that's just a coincidence? Isn't that amazing? Well, the chances of that happening are like 1 in a trillion, so it's never going to happen. It's not by chance. But then if you think to yourself, What if it's the laws of physics? Like, let's imagine you say to your friend, let's say it's Stanley Huxley III, you say to your friend, I think an intelligent agent, probably my mother, put that in my soup, and he says, you are appealing to the concerned parent of the gaps fallacy. You're giving up on science. If we just know more about organic chemistry, if we just know more about the physics of boiling water, I can explain that message. Well, clearly that makes no sense because the orders of letters in a sentence have nothing to do with the chemistry of the pasta or the physics of boiling water. The only source of that much information is a mind. Now, can you get some information by chance? Yes. You can get the word Bob or Spot ran maybe. But that's kind of like the immunity system. Your immunity system can create random code which creates antibodies to cling to antigens. So you can get small amounts of information by chance, but you can never get a sentence like that. And if you look at the probability of amino acids forming a protein, particularly a protein that creates a complex reaction, it's far too small to happen by chance on the early Earth and then end up in a cell. So it's a mathematical impossibility. Now, there's a lot of debate on the internet. If you look on the internet, a lot of people say proteins aren't that difficult to get to. And of course, all those people are not experts in protein research, at least not the evolution of proteins. Here's what the experts say. This is a person from the Weizmann Institute. He's an expert in protein evolution. He says, once you have identified an enzyme that has some weak promiscuous activity for your target reaction, it's fairly clear that if you've got mutations at random, you can select and improve the activity of several orders of magnitude. What we lack is a hypothesis for the earlier stages where you don't have the spectrum of enzymatic activities, active sites and folds from which selection can identify starting points. Evolution has a catch-22. Nothing evolves unless it already exists. So you cannot evolve to get an enzyme from scratch. You can only modify them if they already exist, and that's like a protein. Another expert says, overall, what the field of protein evolution needs are some plausible, solid hypotheses to explain how random sequences of amino acids turned into the sophisticated entities that we recognize today as proteins. Until that happens, the phenomenon of the rise of proteins will remain, as Tofik says, something close to a miracle. So again, getting an enzyme or a protein from scratch is essentially impossible on the early Earth. It's too improbable. But the problems actually get worse. Now, what I want to do is before we get there, I want to summarize my points. First of all, molecular machinery is needed to convert one form of energy into the high-energy molecules needed to drive reactions. Life requires a very specific set of interconnected reactions to proceed and other destructive reactions to be prevented. Enzymes, long proteins, drive the correct reactions, and they direct the energy from the breakdown of the high-energy molecules toward the enabling of energetically unfavorable reactions. Enzymes are required. The enzymes are the result of sequences of amino acids containing the right information like the letters in a sentence. Everything in life requires enormous amounts of information. Here's the second problem. If you've got a cell, and imagine a cell happens through some miracle, a cell just forms on the early Earth, all the enzymes you need, the metabolism. The problem is a cell is going to break down very quickly. Something will go wrong. If your house is sitting out there after a few decades, a window is going to break, a door is going to break, you'll need a new roof. So the cell has to constantly repair itself. The problem is proteins do not self-replicate. It's not like your door on your house is going to replicate so you can fix it with a new door. So you have to have machinery in cells to create new proteins. But then you've got to store the information of those proteins. So where do you store the information? And that's what happens in DNA or perhaps RNA on the early Earth. But the problem is the information in your proteins, your sequences, is encoded into the RNA. Now, when I say encoded, what do I mean by that? Well, if you look at a code, it's kind of like Morse code. Who's ever seen Morse code before? It's kind of like you've got dot, dot, dot that represents an S, dash, dash, dash represents an O. So every letter of the English alphabet is encoded into a series of dots and dash. Or if you happen to be computer programmers, perhaps you've seen ASCII code, where every letter, every symbol corresponds to ones and zeros. So there's an encoding that takes place. Well, the exact same process, a synonymous process happens in life. So if you've got, let's say, a sequence of amino acids in a protein, that's an enzyme, you've got to encode every single amino acid into the language of DNA or RNA. So in the case of DNA, in RNA, you've got 4-letter alphabet. It's not zeros and ones, it's not dots and dashes, but it's A, C, T, and G. In DNA, or A, C, U, and G in RNA. So every amino acid has to be encoded into this 4-letter alphabet. And every amino acid corresponds to 3 letters of this code. So for instance, you've got alanine, which is GCA, and then this one corresponds to AGA. So that's encoding just like Morse code. Well, how does that happen? Well, nobody knows, but what has to happen somehow is each amino acid has to somehow attach itself to one of these 3 letters, which is called a codon, and then somehow they all have to link together. And then later on, you have to be able to decode it. Well, there's actually a great video for this, and this video is called, basically the video is called Protein Translation. So I really encourage you to watch this video if you have a chance. Well, what happens is there's a huge problem. Chemists have looked for a long time to see if each amino acid is strongly attracted to the codons, or the set of 3 nucleotides, and that is not the case. So if you have a vat of amino acids and a vat of codons, the 3 letters sequences, you will not see the amino acids attracted more strongly to the associated codons. And that's a problem, because if there's no physical connection between the amino acids and the codons, there cannot be a physical process that does the encoding or the decoding. Because all physical processes require some causal force. Without that causal force, it's a physical impossibility. So the information in DNA or RNA had to be encoded separately from that of your proteins. That's a major problem. Well, again, there's a second problem, and that's the idea of encoding and decoding for the first place. Because before you can encode information, you have to have a code. Because you have to encode information with the same code that you decode it with. Like if you send Morse code, but the decoder has the wrong connection between letters and dots and dashes, you lose the information. Now in DNA, what happens? I'm sorry, in the decoding process, what happens is each amino acid is connected to what's called a tRNA, and the tRNA has the decode key in it. So every amino acid is associated with a tRNA that has the decode key. But they're linked together through an enzyme called an amino acyl, but the amino acyl enzymes connect the right molecules because of the sequence of information that contain them. But if the sequence were different, you could connect another amino acid with a totally different tRNA. So the code is arbitrary. It could have been anything, but it's driven by the information in these special enzymes. Well, that's a huge problem because there are an enormous number of possibilities of how you could do a genetic code. 10 to the 84, which is a really big number. It's like rolling a 10 84 times in a row. And there's no possible physical connection between the encoding and the decoding. What that means is that the information, both in proteins and in DNA or RNA, and the code had to pre-exist the cell, because you had to create proteins and then immediately after create the encoded information in DNA, and immediately after decode the information essentially all at once, or your cell will break apart. So the information in the code had to pre-exist the cell, but the only place for information in a code is inside of a mind which points to design. Now, here's the situation. And let me just kind of read to you this. This is from a physicist named Paul Davies and his associate, Sarah Walker. And Paul Davies has no religious inclination, so he's not biased. But he says, if one insists on attributing the pathway from mundane chemistry to life as the outcome of fixed dynamic laws, then our analysis suggests those laws must be selected with extraordinary care and precision, which is tantamount to intelligent design. It states that life is written into the laws of physics at the beginning. There is no evidence at all that the actual known laws of physics possess this almost miraculous property. He says almost because he's a materialist. On practical grounds alone, we need to remain open to the possibility that the causal efficacy of information may amount to more than a mere methodological convenience and might represent a new causal category not captured in the microstate description of the system. What we term the hard problem of life is the identification of the actual physical mechanism that permits information to gain causal purchase over matter. This view is not accommodated in our current approach to physics. In other words, he's stating he is a world expert, as qualified as anyone in the world to assess that. He says the laws of nature will not produce life. Instead, we need information to pre-exist life, and that information has to force matter into the right configuration. Now the question becomes, based on this, is the identification of design unscientific? Is it God of the gaps? Is it giving up on science? Well, let's use an analogy. Let me first summarize my last points. Proteins eventually break down, so amino acid sequences must be stored or encoded in RNA or DNA. Encoding involves each amino acid being represented by a sequences of nucleotides called codons, like alanine is GCA. No physical connection exists between any amino acid and its corresponding codons, so no physical process could have driven the encoding of the information. The decoding process must use the same code as the encoding, but they cannot have any physical connection. Therefore, the information and code must pre-exist the cell. Well, again, let's talk about, is that scientific? Well, let me use an analogy. Who's ever seen the movie Contact? Great movie. So Contact is about a member of SETI, which is a search for extraterrestrial life. Jodie Foster is playing the scientist. Great, her best role, by the way. And what happens is she sees a signal from space. Now, she sees this signal from space, and what happens is she starts to decode it. And eventually what happens is she figures out that the signal is encoded information for a spaceship, which is a bit different from that, but it's my only non-copyrighted image that I could find. So she sees a spaceship, and of course the spaceship shows evidence of foresight, coordination, and goal direction, and those features always unambiguously point to design. So no one's going to say to Jodie Foster, you know, you can't be sure that that was designed. Perhaps it's from solar radiation, perhaps it's a quasar that's setting off a signal. Perhaps there's some selective process that caused quasars to reproduce and selected for signals that can code the information for spaceships. You can't be sure it was designed because that's an alien of the gaps argument. Well, what do we see in life? We see not a signal from space, but we see information in DNA, or perhaps RNA, and that information encodes not a spaceship, but a nanotechnology submarine that has incredible properties. It has information processing, energy production, manufacturing, auto assembly, feedback control, signaling, automated repair, boundary conditions with control gates, and self-replication. Again, there's been research both by people studying the minimally complex genome that could exist, people like SIM 3.0, and there's been NASA researchers studying the minimally complex self-replicating engineered system, and what they need are the same. I mean, there's obviously more, but there's a minimum functionality in both. So when you see the minimally functional cell, which is too improbable to happen by chance, you see the same features of foresight, coordination, and goal direction. In other words, the evidence for design in the first cell is just as unambiguous as a signal from space showing a spaceship schematic. And again, what does that mean? That means an intelligent agent had to come up with the blueprint for life and then force molecules to instantiate that blueprint, which points to design. So let me just simply summarize my points. What we have is that DNA contains the encoded schematic for the cell in the same way that the signal from space in the movie Contact contained the schematic for a spaceship. A minimally functional cell must have the machinery for numerous processes such as information processing, manufacturing, and the assembly of parts and self-replication, and the cell's processes demonstrate clear evidence of foresight, coordination, and goal direction, which point unambiguously to intelligent design, and intelligence had to create the information for the structure operation of the cell and then construct it in the world. Thank you.
Okay, it is Q&A time. For those not familiar, Q is question, A is answer. That means you come to that microphone right there behind the very handsome Jonathan. Jonathan, raise your hand. There you go. Ladies. Yes. You ask a question germane to tonight's topic. Have your question 2 minutes or less. We are not looking for 10 or 15-minute diatribes with a question mark not at the end. Very clear, very cogent, all right? We're going to start with the man that proves that Justin Timberlake lied because he is bringing sexy back, Jonathan Hall.
Yes.
Dr. Miller. So, as some people are not aware, there has been a consistent debate between BioLogos and the Discovery Institute and the Culture for Center in Science, and it has consistently been in the form of the intelligent designer. At what point or where in the causal chain does the intelligent designer actually intercede? Is it at the beginning with the laws of physics? Is it more fundamental creationism where God directly molds dirt kind of thing? So
Right.
in your opinion, where do you think that actually lies?
Great question. Well, I like BioLogos, and I have a deep respect for the BioLogos. People, I've had wonderful conversations with people like Deborah Harzma and Jim Stump, and they're very sincere Christians, and they're acting out of a desire to help the church, and I admire that. Where we differ is they believe that the laws of physics were designed to produce life. Now, as I demonstrated, that's not true. The laws of physics are not designed to produce life. They are designed to sustain life, because to have a universe that supports life, you're dealing with enormous numbers of details about the laws of physics that have to be just right for life to exist. And that points to a designer who's outside of time and space, who created everything for a purpose. But I believe that the evidence is very clear that that designer also was involved in the formation of life directly in some way. Because people might argue, and they have argued, that it's more glorious for God to create a universe that could produce life itself. It's like who wants to buy a watch that you have to keep rewinding, right? However, that's problematic because if the laws of physics allowed for the production of life, those laws would have to contain all the information for life. So the laws would be so complex and so numerous and so convoluted, you could never study them. So a universe that could create life would never allow for science. So instead, I believe I'm a Christian, and Discovery Institute is a big tent with people of different backgrounds. Some are religious, some are not religious. We all believe in design, but I'm speaking now not from Discovery, but as a Christian. I'm putting on my Christian hat now. I believe that there's a creator that created the universe for the purpose of supporting life, but that creator also wanted us to do science. So for us to do science, the laws of physics have to be relatively simple and few, and they're very eloquent if you look at like Schrodinger's equations or things like that. Now, also, the metaphor of a watch or a clock isn't good. I think a better metaphor is a flute. A flute maker can make a beautiful flute, but it's designed to interact with the flute player. So our universe was designed to support life, but is also designed for the creator to interact with it, to infuse it with information at different times. So the origin of life, you see in undeniable infusions of information. Also, if you look at things like the Cambrian explosion, would you please switch, if you could just, go into slide 90, please. Look for the fossil record if you could. Oh, I'm sorry. If you could go to 82, hit 82, enter. Just hit 82, enter. Thank you. What you see in the fossil record is not a gradual unfolding of life over billions of years, but you have cells that go all the way back to the beginning of our Earth where it's sustainable. You've got some very strange creatures called the Ediacanarian fauna. You've got things like sponges, maybe a mollusk. But then, in a period of, at most 20 million years or so, you see the first representatives of most of the animal body types that we know about. And then if you look at what's called the Cambrian explosion, there's little mini explosions. So if you look at the resolution of the fossil record, what it tells you is you have entire phyla appearing within 10 million years. Now, that might seem like a long time compared to waiting for Starbucks coffee, right? In fact, just to give you a sense of the strangeness, these are all new phyla, which basically are new body plans, like something like the first time you see a trilobite or a vertebrate. It appears in the fossil record, and what you don't see is millions of intermediates going back to the trunk of a tree. Well, this little period here is within, 10 million years, and that seems like a long time. But there's actually a paper out by Durrett and Schmidt on the waiting for two mutations with applications to regulatory sequence evolution, the limits of Darwinian evolution. These are staunch evolutionists. They desire to defend evolution, yet they found in their paper it takes roughly about 9 million years for two coordinated mutations to appear in fruit flies, which have large populations and very short lifespans. So in the entire time that a phylum came into existence, you only have time for two mutations if they're neutral. And all mutations ever observed, which significantly alter the body plan, are harmful. What that tells you is that there's evidence of infusions of information, not just at the origin of life, but at the Cambrian explosion and other major features of the fossil record. So the difference is we don't just believe in design in the laws of physics, but we believe that the designer is active in creation, infusing it with information. That has huge theological ramifications. I'm speaking again as a Christian, not from discovery. But I think it really points to the type of God we're dealing with, because the God is outside of time and space, but also imminently involved in creation, and imminently involved even in human DNA, which means that that Creator really loves and cares for us, which is incredible. Thank you.
Dr. Miller, John Lepp from Florida brings up something that I'm sure is being discussed in bars everywhere. Dr. Ken Miller, Brown University, claims that type 3...
Oh, gosh. Yeah.
Well, I'm just the messenger. Secretory systems, TTSS, have been found within the flagellum. K. Miller concludes, the existence of the TTSS in a wide variety of bacteria demonstrates that a small portion of the irreducibly complex flagellum can indeed carry out an important biological function. Since such a function is clearly favored by natural selection, the contention that the flagellum must be fully assembled before any of its component parts can be useful is obviously incorrect. What this means is that the argument for intelligent design of the flagellum has failed.
You know what's really funny? Did you ever buy one of those wind-up toys? And you kind of pull the string, it's like, hi, I'm Cowboy Bob. It's so interesting because did I mention irreducible complexity once in my talk? Did I mention the flagellum? So what happens is, and I don't want to be mean, but I shouldn't have drunk that beer, I'm sorry. What happens is when people are trained in science in a secular institution, they're not simply trained in science, but they're given a catechism in a religious faith. and that religious faith is materialism. And what happens is the human brain is designed to detect design. What happens, though, is people go through cognitive conditioning. You ever see The Manchurian Candidate? They go through cognitive conditioning to not see design. And they're sort of given what I would describe as catchphrases. They sort of have implanted phrases, so whenever they are confronted with arguments they can't deal with, the cognitive shuts down, the emotional kicks in, and then these random catchphrases come out. Oh, irreducible complexity has been disproven, which has nothing to do with what I talked about. Isn't that interesting? But that's fine. Let's talk about irreducible complexity. One of the challenges in the discussion is that it's kind of like this. Anyone ever familiar with Manny Pacquiao? He's a boxer. He's a heavyweight boxer, obviously not as popular here as other parts of the country. And imagine you hear about a grudge match between Manny Pacquiao and Daniel Radcliffe, who's the actor for Harry Potter. Now, you think it's a little bit mismatched, but then you find out that Daniel Radcliffe broke 2 of his legs and 1 of his arms. And you say to your friend, you know that Manny Pacquiao is going to win. And your friend says no, because Daniel Radcliffe will pull out his magic wand, he'll turn Manny Pacquiao into a rat and step on him. Now your friend is confused because he's confusing Daniel Radcliffe in the real world with Harry Potter in the fantasy world of Hogwarts. The challenge is people that believe in design want to talk about real evidence and what really happens in the real world in real experiments. Critics want to talk about what they imagine to be true in an imaginary world. So the idea of irreducible complexity is you've got a lot of machines like the flagellum, which is like a motorized outboard motor of a boat, which have dozens of parts, and all those parts are necessary for the flagellum to work. So how can Darwin produce them? Because it requires a step-by-step process for Darwinism to work. 1 part, 2 part, 3 parts, 4 parts. But the flagellum has to have all the parts or it won't work. That's the challenge. Well, the explanation is maybe you can borrow the parts from something else, like a type 3 secretion system or something else. The problem is it won't work because here's an analogy. Anyone ever try to put together an IKEA piece of furniture? Now, even imagine you have all the pieces of your furniture and you hide different pieces throughout your house. And you, again, get a pet chimpanzee named Huxley, and you train Huxley to grab random pieces from the house and try to assemble them into something that works. What's the likelihood of Huxley grabbing all the pieces of your cabinet, bringing it together, and assembling it properly? 0. Because assembling machines requires that all the pieces have to be in the right place, they have to be configured in the right way, and the flagellum requires molecular tools to put them together. So again, the co-option argument is a really great argument in one's imagination, but it never works in the real world. There's no experiments where you see a bacteria adding a piece to an existing molecular machine. Now, the problem is even worse. Let's ignore all those problems. I'm such a generous guy and I've had too much beer. So let's talk about what it takes to put 1 piece on the flagellum. That would be like your propeller. What you would need is, let's imagine the protein is there. What you have to do is give the propeller a regulatory region that launches it at the right time. So that's like 2 mutations. You've got to give it a signaling sequence so that the protein can enter a special gate in the flagellum to get to the place of assembly. That's like 3 more mutations. You also need an assembly tool. So you need another protein with another regulatory region, with another signaling protein, so that the tool goes through the flagellum right before your flagellar protein, and then it gets assembled properly. So you're talking over a dozen mutations that have to happen at once. Because if you just do a couple of things without the others, you actually hinder the production of the flagellum, so it's a selective disadvantage. So the probabilities are astronomical to add 1 piece, let alone multiple pieces. So the whole co-option argument, as most evolutionary arguments, collapses when you look at the details and the mathematics. Applying a mathematical analysis to a scenario like that is like applying intense sunlight to a vampire. It immediately dissolves. Thank you.
Dr. Miller, thank you so much for coming. So I was just curious. I heard a guy once say that I I reject evolution, but I don't reject all forms of evolution.
Oh, great
like
question.
Micro, macro.
Right.
So I was curious what your thoughts were on that.
Could you skip to one slide, please? The next one. Okay, what you have in evolution is, you can think about evolution in terms of what's called a fitness landscape. That's like you've got a two-dimensional field where every point on this plane is like a different organism. You've got an elephant, an ant, a bacteria, whatever. Okay, that makes sense? So this is all the different organisms. The height represents the fitness of the organism. So what happens is you've got these enormous mountains, valleys, and then new mountains. And the top of the mountain would be a very complex, rugged fitness terrain that could be co-evolving and changing. If you look at every species, what you find is you have a genetic variety for small-scale features, eye color, height, things like that. So what can happen is natural selection is true. It's a completely successful theory. It only explains very small changes because there's no genetic variety for the architecture of an organism. All humans have the same basic architecture. That's true with all species. So the other problem is that all mutations that affect the body plan, the architecture, take place in development. In fact, the basic architecture, you have to change the development very, very early. All mutations that affect early development that you can see the effects, if they're dramatic, are harmful without exception. In fact, there was actually an expert in the field called Eric Davidson. He's worked with what are called developmental gene regulatory networks. Those are the genes that control the development of things like sea urchins, starfish, things like that. He's a secular developmental biologist, a world-class expert. He says these things can't change. All mutations that affect the development of the architecture are harmful. He said, who's not at all religious, the small-scale changes in microevolution cannot explain the large-scale changes we see in the fossil record. I was recently, about a year ago, went to the Royal Society of London's meeting on new trends in evolutionary biology. The director of the meeting, one of the directors and organizers, whose name I won't mention so he won't get hate mail, his first talk said, "We now know natural selection and mutations, or the neo-Darwinian synthesis, or the modern synthesis, or whatever you want to call it, can only explain small-scale changes. It cannot explain large-scale morphological changes or new body plans." In this meeting, they talked about other possible auxiliary hypotheses. Through the conference, and it's all online, you can listen to it for yourself. You may need help from a mathematician or biologist, but still, you can still do it. Every single alternative hypothesis, mechanism, either it could only explain superficial features, things like phenotypic plasticity, niche construction, epigenetics, or the talks were incredibly abstract and completely divorced from physical reality. Evolutionary biology, in terms of large-scale changes, is intellectually bankrupt. That's the situation, although small-scale evolution works beautifully.
So this is an odd question as you sip your beer.
I mean, it needs some more beer. Just give me a second.
Drink some more beer. So the general question is 2 books you would recommend on the subject. I'd like 2 books you'd recommend and 2 books you would say avoid. 2 books that don't contribute anything beneficial.
Right.
That if you want to actually know it, don't read these books,
right.
Read these 2.
Right. What I would recommend is Signature in the Cell is obviously a great book. It really deals with these issues. Do you mind if I do 3 books? Okay, that means all I want. Great. Another great book is Darwin's Doubt, both by Stephen Meyer. Excellent books. Another very nice book on the protein issue is Douglas Axe has a book called Undeniable. Douglas Axe. So those are 3 really, really good books to start with. Oh, a beautiful book. Oh my gosh. If you want to go simpler, J. Warner Wallace has a book called God's Crime Scene. Beautiful book. So I'd recommend those. And if you want to avoid books, and I wouldn't avoid any book, but I would just not take things at face value. Like if you look at books by Ken Miller, most of the anti-intelligent design books, what happens is they don't engage our arguments, they engage mischaracterizations of our arguments, straw men. And it's not because they're intellectually dishonest, I hope. What happens is when you're socially conditioned to reject design, it creates filters that distort reality like a funhouse mirror. So what happens is many people, when they engage arguments they can't deal with, their emotions kick in, their intellect shuts down, and their brain distorts the arguments, and they don't even engage with what they're reading. So a lot of the criticisms are distortions of our arguments and not our arguments themselves. I'd encourage you to read all the books, but read them in tandem to see if what they're saying is really critiquing what we're really saying.
A question submitted online by Dr. Martin Pony at UT. Could someone ask him about attacking a straw man with a discussion of origin of proteins, since current thinking is that the RNA world can, before proteins and RNA, can both carry the information for its replication and be an enzyme at the same time?
Sure, the RNA world.
And I'm not sure what I even asked you.
Oh, no, it's a good question. Okay. What happens is I talked a lot about protein translation, and I talked about enzymes, and that was more of a protein-first scenario. Another scenario is called the RNA-first scenario, the RNA world. So the idea is that RNA formed first. It acted like enzymes. A cell formed, and suddenly the proteins swapped out the enzymes. The problem is there was no nucleotides on the early Earth in significant abundance. That's a chemical impossibility. You look at James Tour, you look at any really savvy organic chemist, and the difficulty of getting nucleotides is that you've got to have dozens of steps in chemical reactions where you tightly control the conditions, where you purify them, you concentrate them. So translating that to the early Earth would be fantastically improbable scenarios. Let's ignore that. Even if you had lots of nucleotides, they don't naturally link together into long chains. In addition, all of the reactions that produce these things produce byproducts that would poison the rest of the origin of life. Even if we ignore all of that, the chances of you producing the right enzymes that drive the right reactions to create metabolism are fantastically improbable. It is essentially impossible. So every step of the RNA world will not work. In fact, nearly all origin of life researchers who are not in the RNA world camp talk about the impossibility of the RNA world. But Stephen Meyer goes into a lot of that in Signature in the Cell. Oh, and finally, even if I ignore all those problems, your ribozymes have to order the nucleotides in the right sequence, so you still need information. You cannot escape information, and the probability of getting that much information at once, again, is the example of like the basketball analogy I used. Okay.
Final question. How can we pray for you, your family, and your work with the Discovery Institute?
Could you say that again, please?
How can we pray for you, your family, and your work at the Discovery Institute?
Thank you. The Discovery Institute is working on some of the forefronts of biology research, physics research, and so forth. So we're working on some of the most exciting research that's out there. The challenges are scientists can't tell anyone or else they'll come under terrible opposition from their colleagues. Like one of our colleagues named Gunter Beckley is a world-class paleontologist. And he mocked intelligent design. In fact, he was in charge of the Darwin Day, essentially, in Germany at his museum. And someone said, why don't you read those intelligent design books that you're criticizing? And he made a horrible mistake. He actually read them. And he made a second terrible mistake, which I encourage those out there that don't want to believe this, don't make this mistake. He read it open-mindedly. And what happened is he then became an intelligent design proponent. And as soon as he did, he was fired. So our biggest challenge is getting the arguments out there, because most people don't want to stand up to the criticism. Anyone see the movie, The Darkest Hour? Yeah. Yes. What was interesting is Winston Churchill was being pressured to cave into Hitler. I'm not saying that the critics are like Hitler. That's not my point. But what I'm saying is there was so much fear and so much pressure, they said, let's just give up. It can't be that bad, can it? And then Winston Churchill said, "No, we've got to fight. You don't try to have a conversation with a tiger when your head is in its mouth." And the challenge is many people just want to give up the discussion because they're intimidated by the scientists. But the reality is the science is paper thin, and the evidence for design is overwhelming. So pray for us that we can get the message out there, and people would have the courage to not be intellectually lazy and give in to fear of man, but actually listen to the arguments, and pray for protection, because It's so stressful, and there's so much opposition just for our health, for our wisdom, and particularly just for the ability to get the papers published. Thank you.
Dr. Brian Miller. Thank you, sir. Join us on Facebook. Thank you, World of Beer. Please come get a mug or a t-shirt. Good night.